Welcome to the Ontario High School Video Podcast. This is titled Hess's Law Part 2, but those of you in on the secret know this is actually Part 3 because Part 1 was divided into A and B parts. But this is Part 2. We're going to be calculating the enthalpy of reaction through an examination of a series of related reactions. Now in the previous parts, 1A and 1B, we looked at calculating enthalpies of reaction based on using the table of the enthalpies of formations for the reactants and products and their relationship. In this one, we're not going to do that. We're going to look at reactions that are related. And so come along for the ride. If you understand this, this can be very helpful to you as you pursue your dreams of chemical greatness. The first reaction we're going to look at is the reaction of nitrogen monoxide gas with a free oxygen atom in a gaseous state, and we're going to form nitrogen dioxide gas from that. So we're going to look at these reactions below. Three different reactions that combined together can give us the overall reaction that we're interested in. So the first one is nitrogen monoxide reacting with ozone to form nitrogen dioxide and oxygen gas. The second reaction is ozone gas decomposing to 3/2 oxygen gas, and then finally oxygen gas decomposing to oxygen atoms. Well, first we're going to flip or reverse any of the equations necessary to line up the reactant and products in the reaction table with the reactants and products in the overall reaction. The top equation in the reaction table is fine, but the middle and bottom reaction need to be flipped. When we flip those, we need to make sure that we also change the sign. So negative 142.3 becomes positive 142.3, and positive 495 becomes negative 495. Once we have flipped the reactions and gotten those lined up, we want to examine the reactions in the table to ensure that the coefficients match those in the overall reaction and adjust those as necessary. So as we look at doing this, it looks like the equations in the top and middle are fine, but for the bottom equation, we have two O's and we need just one. So we're going to multiply that reaction by 1/2, the coefficients of 2 and 1 by 1/2, and then we also need to multiply the delta H of the reaction by 1/2 as well, and you'll see the results in the next slide. So here are the results of multiplying by that the coefficient. We now have O yielding 1/2 O2, and instead of negative 495 kilojoules, we have negative 247.5 kilojoules, and this gets everything for our final reaction to match up with the coefficients in the reaction table. We're now ready to add the reactions and the enthalpies together. First, we want to cancel what's the same on both sides. On the reactant side, in the top equation, we have ozone, which is O3. It's also on the product side in the second reaction, so we can cancel the two O3 molecules or moles. We have O2 and 1/2 O2 on the product side, and 3/2 O2 on the reactant side. Those will cancel each other. So we're able to add what's left over so that we get NO plus O yields NO2, and that is the same as the reaction that we were interested in. So we've added those correctly. We then just need to add the heats of reaction. So we add those together, negative 198.9 plus positive 142.3 plus negative 247.5, and we get an overall enthalpy of reaction of negative 304.1 kilojoules. Now, if we were able to do the NO plus O yields NO2 in one step without going through 3 steps, its enthalpy of reaction would still be 304.1 kilojoules. Whether you get there in one step or 3 steps or multiple steps, because enthalpy is a state function, the overall net change in enthalpy will be the same no matter how you get there. So here it is. The enthalpy of this reaction is negative 304.1 kilojoules. What this means is that it is an exothermic reaction in which 304.1 kilojoules of heat is released to the surroundings. Let's do a sample problem. Use the information contained in the following table of heats of combustion to determine the enthalpy of formation, delta HF, under standard conditions, of methanol from its constituent elements. Now, you're probably wondering, where is this table of enthalpy of combustions? It's on the next slide. So when we go to the next slide, I would recommend that you write down that table of enthalpy of combustions, that you do this problem, and then resume the podcast after you have tried to solve the problem on your own, and we'll see how you do. But we'll take a look at the next slide first. Here's the table of relevant combustions that can be used to help solve this problem. The reaction of the formation of methanol, CH3OH, from its constituent elements is written above. So again, I want you to pause the podcast and use this information and what you know about Hess's law to solve. And when you resume the podcast, we'll come back and look at the solution. Good luck. Welcome back. Let's see how you did. Well, the top equation has to be flipped. So you can see that we flipped the equation, and we've also changed the sign from negative 726.4 kilojoules to positive 726.4 kilojoules. And we do that because we have to have methanol, CH3OH, on the product side. The middle equation is okay. We do not have to flip the middle equation. It's set up correctly. And we also do not have to flip the bottom equation. It is also set up correctly. However, we may have to do something in terms of the bottom equation, the H2 plus 1/2 O2 yields H2O, because in our enthalpy of formation equation for methanol, we need to have 2 moles of H2. So we will have to multiply that equation by 2. And when we do that, we will multiply as well the negative 285.8 kilojoules by 2. So we end up with 2H2 plus O2 yields 2H2O. Now, we need to add these equations together and cancel what's the same on both sides. And you can see that we can cancel the water. We can cancel the CO2s. And I think that really is all we need to cancel, except for we have 2O2 on the reactant side and 3/2 O2 on the product side. When we cancel those, we're still going to have 1/2 O2 left over on the reactant side, and that's necessary to have. So let's go ahead and add these, and when we do, we get C plus 2H2 plus 1/2 O2 will yield CH3OH. And again, in enthalpies of formation, fractional coefficients are not only acceptable, they're welcome, because we always want to try and calculate the enthalpy of formation for 1 mole of the compound being formed. When we add the delta H's together, plus 726.4 plus negative 393.5 plus negative 571.6 gives us an enthalpy of formation for methanol as negative 238.7 kilojoules per mole. So one more time, we want to take a look at the end result, and I want to emphasize one more time that when canceling the oxygen, there are 2O2 on the reactant side, 3/2 O2 on the product side, so they don't cancel completely. 1/2 O2 is left over on the reactant side, and that 1/2 O2 is needed in order to form the methanol. It needs that oxygen. So Look closely at that. If you did not do this correctly, I would recommend that you rewatch the podcast, the first part, and when you come to this problem, pause and work it out without referencing your old attempt at the problem and see if you can get that together. Very important that you be able to do these type of problems to have success in advanced chemistry. Thanks. Well, we've come to the end of formally part 2, which is really part 3. If you've watched part 1A, part 1B, and part 2, I'd like to leave you with a quote by Eugene O'Neill, famous playwright, from his play Strange Interlude. "Happiness hates the timid, so does science."